there, ATSEVS533 students, Dr. John Truggy here, and we're continuing now to talk about the stuff in Module 2, the physics of climate and radiative transfer. And over the course of this module, we've been building this idea about how things that can happen due to people, anthropogenic changes, can result in a radiative forcing that can produce changes in the temperature at the Earth. And we're going to kind of dig into the nuts and bolts of that a little bit more with more of an environmental science application to it now. Just to sort of frame up what we're doing here, remember, if the surface of the Earth were truly in some kind of energy balance, which we know we're not quite, but we're awfully darn close. I mean, remember, the total imbalance was like a fraction of a watt per square meter. But if the Earth were truly in some balance, then the energy in to the system, primarily in the form of shortwave radiation from the sun, would be exactly balanced by the amount of energy going out of the system, primarily in the form of long-wave radiation being emitted by the Earth atmosphere system. And what would be determining that value of E out, if we were exactly in radiative balance and everything was a black body and all that good stuff, would be the temperature of the Earth atmosphere system, in particular the temperature of the surface of the Earth ultimately. But if there is not exactly a radiative balance, then there is going to have to be some net heating at the surface of the Earth, as we see on slide 5. Now, this happens all the time, right? I mean, right now it's daytime outside as I look out my window right now. The temperature of the Earth is increasing because there is more shortwave radiation from the sun in the system than there is long-wave radiation being given off by the ground. But at some point, the sun will set, then the shortwave radiation being received from the sky, the energy in will be zero, and we'll still have the ground emitting long-wave radiation and clouds emitting long-wave radiation, and we'll have a negative energy balance and the temperature will go down. Obviously, on a climate context, we have to average all that out. Same with like the difference between winter and summer, where we have to have, in the winter time we are receiving less energy from the sun, primarily because the sun angles are lower and the days are shorter, as you learned in like ATSEVS533. Whereas during the summertime, the days are longer, the sun is higher in the sky, and we receive more radiation. So averaged even over the course of a day, each day is a little warmer than the day before, averaged over all the locations on the northern hemisphere and all that kind of good stuff. So, over climate timescales, on the order of like decades and so on, what's going to happen is to obtain some kind of long-term energy balance, we're going to have to adjust the surface temperature of the Earth. Well, as scientists, we're not talking about like something we're going to do. The temperature of the Earth needs to change until it is emitting radiation at such a rate that once again we have obtained some kind of energy balance, and energy in and energy out again match, but it can't be stressed enough that that takes time. That is not something that's going to happen in the blink of an eye. It can be, even some atmospheric scientists have trouble understanding that because they think, well, wait a minute, literally hour by hour, the surface of the Earth makes adjustments to its temperature as the amount of radiation from the sun during the day is greater than the amount of long-wave radiation the surface is emitting, therefore the temperature goes up, but that's true. But to obtain a balance for the whole Earth atmosphere system, the ocean, the deep ocean, ground moisture, the clouds, the aerosols, and so on, that's going to take time. In much the same way, earlier in this module, we used an example of a pizza. How about a turkey? We put a turkey in the oven, okay? If we put this turkey into a hot oven when the turkey is raw, it takes time for the turkey to come to the same temperature as the oven around it. There is immediately a radiative forcing on the turkey. It's not entirely radiative. There's a combination of factors that are changing the temperature of the turkey as it cooks. But to a good approximation, we can talk about it as a radiative forcing, where we could say, we had the turkey sitting on the countertop had a certain radiative balance going on, and that, with the radiation it was receiving from the room around it and so on. But when I put it into the oven, there is a new radiative balance immediately. Well, not new radiative balance, a new radiative forcing. Okay, we have changed the energy balance, and we have a net positive radiative forcing on the turkey, but it's going to take time for that turkey to warm up. The time lag between putting the turkey into the oven and it's being cooked, well, cooked is a more complicated chemical idea than just being warm. Let's just say being warm is a manifestation of a property called the thermal inertia of the turkey in this case. Thermal inertia is a word that physicists hate. I mean, if you just like Google define thermal inertia, you get this lovely thing. It's the degree of slowness to which the temperature of a body approaches that of its surroundings, and it's dependent on a lot of factors, including the absorptivity, the specific heat, the thermal conductivity, its dimensions, and other factors. And you can imagine that like a physics student hates that idea. They like to, thermal inertia is broadly, it's kind of a layperson's idea about it takes time for it to heat up. Obviously, in like a physics thermodynamics class, they would actually want to pick this apart and figure out, is it because of how it absorbs radiation? Is it because of the specific heat? Like how many joules of heat it takes to increase the temperature of a kilogram of that material by 1 degree Celsius? A physicist hates that. But the broad idea here of thermal inertia is sort of useful. It takes time to heat materials. And different materials take different amounts of time, as we're going to see in one of the questions that I'm going to ask. Alright, well right now we know from previous lectures in this module that the Earth is not quite in a radiative balance. We have some net radiative forcing going on, and it's somewhere in the range of 0.6 to 0.9 watts per square meter. 0.6 was the number that we picked off of that slide from NASA. Other textbooks using slightly different observations get numbers as high as like 0.9 watts per square meter. Somewhere in that range is where the Earth's climate system is right now, which means that right now the surface of the Earth is absorbing more radiation than it is giving off. We are not exactly in radiative balance. There is some new temperature that the surface of the Earth is going to need to reach for the surface of the Earth to now be emitting enough radiation by Stefan Boltzmann's law that it would now balance this again. The surface of the Earth overall, over all the square meters of the surface of the Earth, would now be emitting about another 0.6 watts per square meter, maybe as high as 0.9 watts per square meter. There is a new temperature that the whole Earth is going to have to warm up to. We're not there yet. If we were there yet, we would be emitting as much radiation as it took to make this balance have zero. We would now be in radiative balance again. So at the current rate of warming, the rate at which the Earth is warming due to its thermal inertia, it's going to take several decades before we achieve that new temperature. We have warmed the planet by a certain amount, in the ballpark of 1 degree Celsius, as we learned back in Module 1. Even if we stopped emitting any greenhouse gases right now, we would not be in radiative balance yet. It would take a few more decades before the temperature would have increased enough that our committed warming would be reached. We would have reached the temperature it's going to take to be in equilibrium with the greenhouse gases we have in the atmosphere now. Even if we stopped, even if right now all greenhouse gas emissions stopped, we would continue to have the temperature increasing based on what we've already put up in the atmosphere. And we can't do a damn thing about it. We've got to work on the assumption that's coming no matter what we do now. And that is fascinating from like an environmental policy point of view, because it makes it very difficult to address the issues of global warming from a policy point of view, because the benefits of reductions in emissions today aren't realized for decades to come. Even if we stop burning fossil fuels, there's still a whole lot of warming to come. Yes, if we stopped burning fossil fuels, that new equilibrium temperature won't be as high, or whatever, but that's decades away, and that is really hard. It's really hard for policymakers to make policies that involve making sacrifices today for things that won't happen for decades to come. That's just a policy issue, okay? People who make policies have hard times convincing their constituencies that that's a good idea. Now, just to kind of refresh, because we're going to be talking so much about radiative forcing in this lecture here, this idea between this imbalance between the energy in, E in, and the energy out, E out of an object, and the time it takes bring that system back into balance is all kind of, that brings us back to this notion of radiative forcing. Now, we're going to use a slightly different, it means the same thing, but a different way of articulating the definition of radiative forcing here, or RF, where RF is just that change in that balance. It is the change, delta, E in minus E out. So before the change happened, before we took the turkey in and put it in the oven, it had a certain energy balance. It was emitting a certain amount of radiation to the environment around it. It was absorbing a certain amount of radiation from the energy around it. Then we put the turkey in the oven, where a very different amount of energy was going in and presumably out. There was some radiative forcing, the difference before and the difference after. It is the same as what we talked about before when we talked about radiative forcing. We're just sort of rearranging the terms here. Maybe you'll find that definition of radiative forcing a little more to your liking. So, okay, by definition, this idea of radiative forcing is defined to be like before the system has come to its new thermal equilibrium temperature. Once the turkey has been in the oven for a few hours, it will have reached a different energy balance. The turkey got hotter, it is emitting more radiation, its value of E out has gotten bigger. Okay, we're not worried about that yet. Okay, that time dependency of radiative forcing, that's a whole complicated story. Okay, we're talking about like before temperature change has happened. Therefore, radiative forcing becomes a kind of a measure of how much some climate perturbation is going to result in a change in the climate based on the climate sensitivity factor, climate sensitivity parameters, right, word lambda, in the same sort of way that the radiative forcing on the turkey that we put into the oven results in a temperature change in the turkey over a period of time. You could come up with some kind of like turkey sensitivity parameter that would be a measure of how fast the turkey comes to its new equilibrium. Alright, so kind of that first part of this lecture is kind of rehashing some ideas and giving you a few new vocabulary words like committed warming and so on. Let's actually ask a couple questions about that though. If humans stopped releasing anthropogenic greenhouse gases into the atmosphere right now, the temperature of the planet would A, continue increasing until all those greenhouse gases were removed from the atmosphere. B, continue increasing until a new equilibrium temperature of the planet was reached. Or C, stop increasing and stay at the current temperature. What would happen if we stopped adding greenhouse gases to the atmosphere right now? Make a choice from those three options and get a little feedback before you move on to question 2.